Okay, so plotting these points, we get something very much like this. And notice that every time x goes up by 1, this is multiplied by almost 3. So it's going to go almost 3 times as high if you move over just 1 unit here, and then 3 times as high as that, and so forth, and that's easy to understand. What happens as you go to the left? Well, every one of these numbers will be divided by about 3. Okay? A little less than 3. So it gets 1/3 as high, then it gets 1/3 as high, and 1/3 as high, right? So, I'm going to say 3 times as high, approximately 3 times as high. Every time x increases by 1, right? Approximately 1/3 as high every time x decreases by 1. Okay, is it ever going to be negative? Can you ever get a negative by dividing these numbers by the same number again and again? Not if it's a positive number, and it is. Okay? So there's your graph of e to the x. Okay, well, natural log of x. There's a table for the natural log of x. It's the inverse function. It means that you switch x and y. Okay? So if you take a value of x like -2, and you get e to the x is 0.13, right? Now you do the natural log of 0.13. Natural log of 0.13, well, that means if x is 0.13, what's the natural log? It's -2, right? Which means that if you start with -2 and do the e to the x, and then take the natural log of that, you get the same thing back. Okay? And that occurs for any x. With restrictions on the domain. Okay? There's no restriction on the domain of e to the x. You can do e to any power, but there is on the natural log because you can't have any negatives over here. Because the numbers here are the values of the exponential and they're all positive. And the graph of the natural log function then, you can confirm, is going to look like this. Now, here the x-axis is a horizontal asymptote. Say the negative x-axis, right? Over here, negative y-axis is vertical asymptote. Okay? So now let's put epsilon over here somewhere close to 0. What's the natural log of epsilon? Okay? Natural log of epsilon is some negative number as long as epsilon's on this side of 1. Because of course here is the point where x equals 1, because you have the point 1, 0. Okay? Now what happens if you get closer to 0? What happens to the value of the natural log? It gets more negative. It gets bigger, but it's negative. Okay. Bigger, it gets less. Okay? But bigger refers to the absolute value of the quantity. So you want to be careful, but I know what you meant. Okay? Yeah. This point is going to go down, right? Is there any limit to how far this point will go down as epsilon approaches 0?
Zero is the limit?
Well, this function isn't even defined when epsilon equals 0, because there's no 0 in this column. There's no 0 in this column, right? Yeah. So there's no 0 here. Okay? And the fact there's no 0 here means 0 isn't in the domain. The natural log is not defined at 0. It's not undefined because of anything it does. It's undefined because there's no 0 in the e to the x values. And the values of e to the x become the x values for the natural log. Okay? So epsilon can't ever, epsilon can reach 0, but as soon as it does, it's out of the domain and you can't even talk about the value. But what happens as epsilon approaches 0? Well, this is an asymptote, right? Keeps going down, but it never touches the y-axis, right? So the further you move towards 0 with epsilon, the bigger the negative number you get, and there's no limit to how big that negative number will get. Okay? So, the limit is undefined. Well, actually that's it. The value of natural log of 0 is undefined, but the limit is badly written negative infinity. Okay? And of course, this limit is negative infinity, but it's minus this limit, so the limiting value here is infinity, right? So the area of the 1 over x curve, as you get closer and closer to 0, exceeds all bounds. Okay? So, what we're talking about now, the picture would be, if this is your 1 over x function, and it's asymptotic up here. Okay, here's your epsilon. What we did for the integral it's this area, right? Okay? As epsilon approaches 0, area approaches infinity, meaning that any area you want to get, no matter how big, you can make epsilon small enough that this integral will give you that area. So I can say that this means that the integral from epsilon to 1 of 1 over x dx be equal to any positive value no matter how great. Okay? If you choose the right epsilon. Okay? I probably should have said that. If you choose the right epsilon. Or more importantly, it can exceed any number, no matter how great, just by letting epsilon be small enough. Okay?